Welcome everyone, come to my section today. My talk is about exploiting EDCA for feedback channel in a hybrid VLC and Wi-Fi architecture. So let's first talk about why we need VLC for indoor communication. Is that the future of wireless communication is depend on the smaller cell, because we want to increase the network capacity and the efficiency to create the cell-free communication. And that is exactly what VLC is. Besides that, VLC can bring a lot of benefits such as spectrum efficiency, energy saving with a low-cost implementation. And due to the popularity of LED LED right now, by integrating the communication element into that, it can bring the much broader impact in the indoor environment right now. As you can see on the right hand side, in this indoor scenario for visible light communication, can achieve a 35 gigabit per second. That is really showing how much potential that VLC can do. However, we still have to facing some challenges such as a narrow field of view, a rotation disalignment, a high SNR variability, or even with the uplink solution when the light is on. And why we come up with this? With the hybrid architecture, the first question is that, can we solve the coverage and the uplink issue by exporting the coexisting Wi-Fi network? Even though the Wi-Fi signal is much more stable, but we still have to facing with the limited bandwidth and potential interference, where with the VLC we don't have to worry about that anymore. That is where reference scenario for the hybrid architecture is showing up on the right hand side. That we have multiple VLC access points, in this case, coexisting under one Wi-Fi network. On the light bulb, the LED bulb in this case is embedded with the VLC transmitter. And on the lighting system is connected to the local network area through Wi-Fi access point. In the receiver side, we have VLC receiver with two interfaces, VLC interface and Wi-Fi interface. In order to solve the uplink issue, that is where we use the Wi-Fi network area. So we don't have to worry about that anymore. In this case, the intelligent control unit is one of the main controller, manager, and optimizing the whole network. So what we're seeing after this, because they have to work with both Wi-Fi and VLC network, the coupling effect can be happening. When the VLC downlink performance can really be affected by the Wi-Fi network condition, especially in a bidirectional connection. When Wi-Fi used to transmit the TCP ACK for the uplink for the VLC connection, and that is where the problem occurs with the multiple coexisting VLC node in the Wi-Fi background traffic. The uplink congestion can lead to a loss or delay for acknowledgement packets for the VLC link, and consequently is reducing the downlink rate for the VLC performance. So in order to recreate this phenomenon, we ran a simple experiment that to create a hybrid VLC and Wi-Fi architecture based on the Open VLC platform. The maximum rate for this platform is 400 kilobit per second. And as you can see on the graph on the right hand side, we want to comparing the throughput of the VLC with different number of background node station over here. The open VLC will use TCP link in this case, and with the background node will use UDP with up to 800 kilobit per second. The open VLC in the curved blue line is that can achieve a maximum rate is 400 kilobit per second with no number of background nodes on the network. However, when we increasing the number of background nodes or the congestion level in this case, the VLC throughput is significantly reduced based on this only by 5 background nodes. That is an alarming issue that we have to find a solution for that. And the red curve is what we're proposing using EDCA Act that I will explain later on. We achieve much better performance in this case. So let's take a look. What is the problem behind the reducing of performance of VLC? And after analyzing, we see that because in a random access network, the VLC have to complete with so many other stations in the network for the opportunity to transmit any packages. That is where, for example, in K over here, VLC only can transmit 1 over n+1 opportunity. So we have to use different options to solve that issue. The first one come up is that with a priority channel access and ticks off. So we can give the much higher priority for on the VLC packages in the Wi-Fi link, and that can give them much more higher chance to transmit during much the same time as in the first case. Another option we can use is with the frame aggregation, is that all the acknowledgement packages can be combined into one big frame to transfer into upper lane. It's going to reduce the contention number or even the MAC overhead that can happen if we transfer it individually. So, in order to experience it in much broader scale, we want to use the simulation to experience this, and that is Network Simulation 3 is taking place. On topology on the left hand side, is similar to what the architecture that we have earlier for hybrid architecture. We have up to n background node station in this case. In our simulation is the 10 unit background node with the same distance from the access point. We use UDP for transmission with 800 kilobit per second for on the background node. Regarding to the VLC link, we use n up to 4 VLC nodes in this case with the TCP transmission with the data rate is 10 megabit per second to experience how much impact that the Wi-Fi channel can create for the VLC link. So let's go to the results and see how much impact this can have. This is the comparison between VLC downlink, Wi-Fi uplink throughput performance. We have two cases in here with one VLC link in the network, and on the right side is 4 VLC link in the network. As a fact that we have 3 different categories over here, with the blue curve with VLC and Wi-Fi using the same accept category. The green curve, we activate the frame aggregation, and the red curve, we use the much higher priority for VLC uplink. It's the video in this case. As you can see on both sides, that the blue curve is dramatically as similar with what we have in the experience case. And by using the frame aggregation or EDCA act, we can achieve much better throughput for overall network, especially in the worst congestion case. With the 4 VLC link and up to 10 background nodes, the performance only reduced by 4%. How about we talk about the uplink end-to-end delay for TCP ACK flow? As similar, we still use different 3 categories for this one. In both cases, with 1 VLC and 4 VLC link uplink, we achieve much shorter delay in both cases compared to the other one. In the background station overall throughput, EDCA will achieve a little bit lower throughput than the other case. But in general, with EDCA ACK, we can clearly see that the performance of hybrid system is much better than the standard one. So after our work and simulation, what we can come up with is that the condition of Wi-Fi is really important for overall network, especially on case with the small feedback frame can significantly reduce the network overall. And after analyzing the impact and different options available at the MAC layer, with EDCA ACK can outperform a frame aggregation in on solution, even though both of them working better than the traditional one. And in the future, we want to analyzing the solution in much complex in K, where with different node mobility, higher complexing priority flow in a multiple coexisting Wi-Fi network. And that is the end of my talk. Thank you everyone for listening.